I am Niels van Hoorn at NVH on Twitter. And I'm here for the third year back in a row, and I just got a little kid, so I really need to convince my wife that I was coming here. And she's a feminist, so I basically told, she asked, well, where are you going? And I said, like, I'm going to Chester, which is basically the gender-neutral version of Manchester. So, and then she agreed. I work at a company called Framer. We build a design tool out of Amsterdam. And I organize my own conference too, which is Swift Island. Let me check if I, oh, sorry. Yes. Yes, perfect. Which is a conference on an actual island in the Netherlands called Texel. And we created it, and to explain that a bit, I created this nice infographic, because you all know the excitement, right? Here, the excitement up to WWDC. Then WWDC starts, and that's a lot of fun. And then the WWDC ends, and you start watching the videos and start rewatching things and trying the API, and that's where your confusion like increases a bit. It's like you don't really know what's happening anymore, and it doesn't really work, like the betas are not as good as you expected. And that's why we created Swift Island, because we have workshops that actually are on the topics of WWDC, so you'll understand it a bit better, and your confusion will go down, and your excitement will go up again. And as you can see, it's even more fun than WWDC. So there are still a couple of tickets left, and if you use the discount code CodeMobileUK, you get a €40 discount. So get your tickets on swiftisland.nl. So let me talk a bit about why I created this talk. So I have a master in artificial intelligence, but whenever I talk to engineers about machine learning, I get the feeling that they find it hard to understand what's going on. Because we are used to giving computers instructions, and then like we expect the computer to do those instructions. But when you tell them that you can like teach it to learn things itself, they get confused. And it kind of feels like magic to people. But it's just another algorithm. So what I'm going to try to do today is basically show you the inside, or like reveal the magic trick to you, just like this person is doing in a bit. I'm going to explain that it's not magic that runs artificial intelligence, but actually it's math. So now I'm going to show you a bunch of functions, which you can ignore. You don't have to understand this. This is only there for reference if you want to go back to it. You just need to know that there are 3 functions that we're going to use, but ignore this for now. And the second inspiration for this talk was Richard Feynman, which was a brilliant lecturer and physicist. And he once wrote on his blackboard, "What I cannot create, I do not understand." And we're going to take that by heart and build a neural network from scratch, so that hopefully in the end we will understand it better. So what are we going to build? Well, a neural network is a network of neurons, and it consists, or a neuron consists of, is modeled after a biological neuron, which is a cell that basically has synapses that fire into the neuron, and then it fires over its own axon. Well, after a certain, like if a certain threshold has been reached. Well, that's the only similarity basically of a neuron in artificial intelligence and biology, because it's a bunch of inputs that have weights, then there is some functions that sums them all, and then if it, and then there's an output function for that. So a neural network is not, an artificial neural network is not a replication of a biological neural network, only something that is modeled after it. So we're going to implement this, but first, don't try this at home. This is just like go to show you how this works. There are people much smarter than I am that actually created frameworks to do this kind of stuff, and I suggest using those instead of my code. Then some cautions, because I am not a robot. So if you're like, I think I spot a bug, or you find yourself making this face, just raise your sword, or if you don't have a sword at hand, raise your hand. And if you feel like Neo, you go, what? Or the Fresh Prince, you're like, what? Or I go full on Shining, and you're like, no! Just stop and ask, and I'll explain it to you. Okay, let's get started. So there was this math that I told you about, and you don't need to look at the implementation of this function. It's there if you're interested in it, but we're going to show the output of this function. So here I have a for loop which is going from -5 to 5, and here's the output of that, the sigmoid function, which is basically a function that maps any value between -infinity and +infinity to 0 and 1. So if we look at the values of this function, you'll see that if the value is minus something, then it is 0. Then at 0 it's approaching 0. At 0 it is 0.5, and then if we scroll a bit higher, then at 5 it becomes 1. So it is basically a flattening function. And well, the graph looks like this, but even if we go from -10 to 10, then you'll see that the graph becomes a little bit squashed down. We can even go to 100, and then get really squashed down. Derived sigmoid is basically the function that is the derivative of that sigmoid. Again, you don't have to understand that. It's just a function that we're going to use when implementing this neural network. So we need something for this network to learn. And for now, we're going to start with some basic Boolean operations. So here I created some basic not, on, or, and XOR functions. And to give you a little bit, let me check, why doesn't this work? A refresher on those, like you have a not function when you input true, then here on the right side, it's the little f there, and I try to, oops. It crashed. So, which says like basically true becomes false, and if I change this into false, then it becomes true. Then we have the OR functions, which if false, false, true, then it is true. And if I change this to false, then it will become false. Well, same goes for the AND function, which is false now because there is this true here. Well, you basically get the point. But what I was getting at was the XOR function, which is a little bit of a weird function where if it is false, false, then it becomes then it becomes false. If it's false, true, then it's true. If it's true, false, then it's true. And if it's true, true, then it becomes false. So it's a kind of a weird function in that way. So let's build this neural network. And for that, we're going to start with a protocol. And the protocol is predicting. And it has one function, which is called predict. And it's going to get some inputs, which are a double. And it's going to give the output, which is also a double. Then we have a protocol learning, which is derived from predicting. And then we learn with some form of error. So we learn from our errors with a certain speed. So now we're going to implement a class that implements these protocols. And the first class we're going to implement is a neuron. And a neuron has a set of inputs, which is a list of doubles. And a set of weights, which is used to actually create the the weighted sum of the inputs. So let's create an initializer for this that we pass the num inputs, which is an integer, and then we're going to create the inputs is actually a array repeating 1. Number is num inputs. Then we have a variable num weights, which is also the number of inputs. And then the weights is a array repeating a double dot random. This is the initial value, num weights. This is the initial value of the weight, so we're going to initialize them with a random number between -1 and 1. This is weights. So now, just to show you a bit, let's instantiate that neuron. Let's create a num inputs. Let's say 3, and we're going to create a neuron that has a number of inputs. And now I have a little visualization for this, so we can show it right here. So what we basically have here is a single neuron, which is represented by the dark blue dot on the right side, which has 3 inputs. And these inputs are connected to that output with 3 black lines, which represent the weights. The thicker the line is, the higher the weight is. And if the line is, we need to have another function that actually sends the data of the weights there. Yes, there we go. So if the line is yellow, that means the weight has a minus, has a negative value. So if I run this a couple of times, you see the weights get initialized randomly, but we actually have a bug here because they are always the same value. And this happens because this array repeating actually executes the value once and repeats that in the array. So I created another version of this function which basically has a auto closure, so it will run the random function every time you create a new element. And here you see we have different weights for the values in here. I can also visualize that here. So you have neuron.weights. And then, oops. Here you see that the first weight is 0.2, which is a black line. Then it's minus 0.18, which is a yellow line, and 0.1, which is a black line again. So, and then if I run it again, you see that like the negative values match up with the other values. Okay, so now we have like created something that is a neuron, but let's let it conform to these protocols. So first we're going to start with predicting. And we're going to implement this predict function, which has these inputs. And then we're going to set the inputs to the inputs. And we're going to return a computed value, which is the output. And the output we're going to implement here, which is the output, which is a double. And for the output, we're going to take the weighted sum of the inputs. So we're going to create a sum, which is a double. Which is 0, and then we're going to loop over all the inputs, and we need the indexes too. So, oops, input. So we're going to call inputs.enumerated, which will give us the indexes, and then we are going to add to this sum the input times the weight that is connected to that input. So the index of that input. And then we're going to return the sigmoid of that sum. So here's one of those functions that I talked about, which will make sure that like every input that has the, I keep forgetting to type the S. So the, which will make sure that the sum, like we're summing random inputs and random weights here, so that can become values that can become really small or really large. So the sigmoid function makes sure here that the output is always a value between 0 and 1. So now we have the predict function. Let's add the learn function too. So let's add the learn. And as I said, we're going to learn from the error. So we're going to create a error term, which is the error times the derived sigmoid. There's the second function of the output. And then for every input, we're going to update the weight. So we're going to iterate over all the inputs again. And we are going to update the weights that is matched to that input. And we're going to add to that the input times the error term times the speed. So this is basically the, oh yeah, we need to, no, basically, errors. So this is the basic implementation of the learning algorithm. The learning speed here is how quickly we adjust to the value that we expected. In machine learning terms, this function is called backpropagate, which is descriptive in what it does, but not like why it does it. And the speed is usually called the learning rate, just to get you acquainted with the terminology in machine learning. So now let's actually use this function to teach our neurons something. So for that we need some examples first. I've created a handy helper function that will create examples for every instance of, or every possibility of a function that you pass it. So we're going to start with the not function. So we have one input, and we're going to pass those num inputs here too. And then if we run it, we basically see here that the examples contain a number of inputs. I'll move this up a bit. Contains a number of inputs, in this case just one, which if it is 1, which represents true, the expected value is 0, which is false, and if it is -1, which represents false, then it's the expected value, which is 1. So this is kind of weird, because in the inputs I represent the false and true as -1 and 1, and in the output, as I said before, like the function always maps it between 0 and 1. This is because this works better, this representation works better in a neural network. In general, when you're using machine learning algorithms, you're always like massaging your data to like actually work best for the problem at hand. So in this case, our representation of the inputs is different than the outputs, but this will make our algorithm work better. So now we have the examples, so we're going to create a teach function, which we are going to pass a learner. And the examples. And then we're going to iterate over all the examples. And for every example, we're going to get the output of our learner. So we're going to ask the learner to predict the examples, example.inputs. Then we're going to calculate a error, which is the example.expected. So this is the expected value of that specific example. And then we're going to subtract the output from that. And now we're going to basically tell the learner to learn from its error. So we're going to pass it its error, the error that we calculated, and then we're passing it 0.3 as the speed, because this is basically a magic number. I've tested it a bit, and 0.3 works for these examples. Again, in machine learning, you're usually just trying this stuff out. You're just testing if a learning, or if a speed, the speed here is, if you have a higher speed, it means it will adjust the network to the data that you pass it more quicker. If you have a lower learning speed, it means that the network will adjust slower, but is also more resistant to noise. So let's check what the error is here. Oh yeah, in the example property, the expected prop here, let me tap that, is actually, it's an array of doubles instead of just a double, because we're going to use this example for a network that can have multiple outputs as well. But now we only have one output, so we take the single value. So now we're going to teach our neuron the examples. And we're going to check what happens. So we're going to check if we have all the examples, if we iterate over them, what the learner thinks, what the neuron thinks the output should be. So we're going to predict the example again. inputs, and then the output, if it's bigger than 0.5, it's true. And then we're going to check the example, what the expected value was, and if it's higher than 0.5, it's true. So let me double check here. Examples. And then I'm going to add a little bit of code here that basically sends the weights to the other end. So now we're going to look at these values here, and you basically see that now the expected inputs is false true, and the expected and the actual output is false true. But if I run this a couple of times, you'll see that at some point now the network didn't learn actually our function correctly, because we only called this teach function once. So what we basically need to do is do this in repetition. So now we're going to take 20 times. We're going to call this teach function, and then it will always have the right value. And to show you a little bit better, I'm going to add a little weight here, and I'm going to instantiate the weights on in an array that is just 1. So now it's going to start out with 1. And then it's going to slowly, like you see the line getting thinner all the time, so the weight is dropping a bit, and now it has become negative, so it actually learned our not function correctly. So it made, like from true, it makes false, and from false, it makes true. So we can do the same for our OR function. And now we need a little bit more neurons, otherwise OR doesn't make a lot of sense. And now I have a bug. Let me double check. Yeah, I updated the weights here. I should remove that. So now it is learning these weights of the OR function, and you see it adjusting to like always positive weights. But if I look at the weights, or if I look at the result here, then you see that there are still a bunch of errors in the actual output. And this is because all the inputs represent Boolean values, and with all the weights that get adjusted, there's basically too much randomness going on, because all the weights can change to true or false. So what I'm going to do is I'm going to add an extra input, which I'm going to add as a variable here, extra input, which is a Boolean, which I set to true by default. And then if I have this extra input, I'm actually going to add an extra weight to the number of weights. And then when we're going to predict and we're going to change the input, I'm going to modify the extra input, or I'm going to modify the inputs, self.inputs, and I'm going to append 1 to them. So this is basically an input that is always 1. So I need to add that to send to the other side, to the view as well. Oh no, wait, I don't need to add it here. So now you see here the gray bubble represents this specific extra input, and you'll see that it gets a little bit thicker. Yeah, it's not really visible, but it gets a little bit thicker weight to basically stabilize this function. And now you'll see that the input or the expected outputs and the actual output actually match up. And then if I change this function to AND, then it will actually learn. Well, that was really quick. Let's stop it again. Yeah, it will actually learn to have a negative value for the input and a positive value for all the other ones. So you could figure out these weights by hand, right? This is not a complex thing. But what I'm showing you is basically the algorithm that is able to figure this stuff out on its own. The only thing that we pass to the algorithm is basically the examples that we've created. So basically we're just saying, like, look at these examples and then figure out the weights on your own. This is like really on a small scale, but like if you make if you put these neurons in a network, then it can actually do much more interesting stuff. So let's try this out for the XOR function. And the XOR function is actually a function. For the XOR, we need 2 inputs. Is a function that can't be learned by a single neuron. So it actually will always get this wrong. That's why we now are going to create a network of neurons. This network consists out of multiple neurons. And we're going to create a class network that has 2 layers of neurons, layer A, which is a list of neurons, and layer B, which is a list of neurons. And let's create an initializer which has the number of inputs for our network, which is an integer, the number of neurons that we're going to have in layer A, and the number of neurons that we're going to have in layer B. Now we're going to instantiate layer A with this repeating function that creates a neuron with a number of inputs, which is the number of inputs. Oh, and this is num_a, number inputs. And num_a is the number of neurons in that layer. Then let's create layer B, which is kind of similar. But instead of the num inputs, it's actually layer B is connected to layer A. Let me quickly set this up so you actually can view a visual representation of this. Let me fix this. So num_a is the number of inputs or number of neurons in layer A, and num_b is the number of neurons in layer B. And now I need to remove this code again because otherwise it gets messed up. And now if I create a network, which is a network with num inputs to 1 output, then you'll see this is the network that gets created. I actually made a mistake in the visualization because here we need the extra input as well. So basically it consists of 2 layers, which are the second and third row of blue dots. And the light blue dots are the 2 inputs. And then we have this extra input, the gray one, for both the layer A and the layer B that now just consists of one node. So now we can adjust this network, or basically conform this network to the learning protocol. But for that, we're going to change the learning protocol a bit, because a network can have multiple outputs. Right now, it has just 1 output, but I can here say, for example, 3. And then you'll see that basically the second layer has 3 outputs. So if it's going to predict, it needs like an array of doubles to specify. So this predicting is going to be an array of doubles, and these errors are also going to be an array. And then the learning doesn't conform to that protocol anymore, but we're going to conform the network to the learning protocol. So now we're going to implement the predict function. And what we're basically going to do is we're going to pass the inputs through the network. So we're going to create a variable layer A values, and we're going to map all the neurons in layer A, and we're going to ask them to predict based on the inputs. And then we're going to get the layer B values, which we're going to do the same. We're going to map over layer B, but the values that we're going to pass, that we're going to ask to predict about, is basically the layer A values. So basically, we're passing in the inputs into layer A. That results in outputs. Then the outputs we pass into layer B, and then we're going to return layer B values. Yeah, we still need to implement the learn function here. But like to visualize that a bit, like we have the inputs, we passed it and like multiplied it by all the weights, and then we get the values that are outputted by the first layer, and then we pass it into the second layer, which results in the outputs. So now we're going to implement the learn function of the network. And what we're doing for that is we're looping over the, we're learning backwards. So basically we're starting at the end. We're basically saying, okay, this is the output that we expected, and then we're moving one step back, and we're adjusting all the weights of the second layer. So we are going to get the index B and the neuron B out of layer B dot enumerated, and then we're going to tell that neuron to learn about error, and then we're going to get the error index error index from the list of errors that we get, and we're going to pass in the speed. And next we're going to do the same for the layer A. So we're going to say layer A, neuron A in layer A dot enumerated. And now we don't have a list of errors to get from. So what we're basically going to do is we are going to, for every connected node on the right side, like you see that every part in the middle layer has 3 connecting weights to that. So we're basically going to get the accumulated error of all those weights, and then basically say that is the error that we're going to learn from. So we're going to loop, we are going to have a variable accumulated error, which is a double that starts at 0. And then for index B, neuron B in layer B dot enumerated, we're going to add to this error the neuron B dot weights, the index of the neuron that it's connected to, times the error that was reported for that specific neuron, which is index B. And then we're going to let neuron A learn from the accumulated error, which I misspelled, but I left that. Leave that in here with this speed. Now let's fix all our problems. So this needs to be neuron B. And in the examples I had this, I took the first thing, and this is errors. So now the teach algorithm basically needs something to have an array of outputs to map to get the error from an array of outputs and array of expected values. I've created a struct called mistake for that, and a mistake you can pass the expected values, so that's the example. Example dot expected, and the output expected. And from a mistake you can actually get the errors. So now instead of a neuron, we're going to pass a network to our learner, and we're going to let it run. Oh yeah, and now I need to basically, like, to visualize this, I need to be able to or I need to be able to send the data again, and for that I need to implement a function or a thing that maps over the layer A dot map, and we're gonna get, oh, it's basically a flat map, I think, flat map, and we're going to get all the weights out of there, and we're going to do the same for layer B. And after we learn, we're also going to send this information. Oh yeah, and there's actually a bug here still, because we're in the learn function, we're first updating the weights of the second layer, and then we're updating the weights of the first layer, so layer A. But we are using the weights of the second layer, we are using them to calculate the error. So we basically need to do that before we update the weights of the of layer B. So we're going to move this to on top of this. So now you see that it's adjusting the weights if I run this code, but the output won't be exactly what we expect from this. And that's because we're here saying, like, okay, just teach it 20 times, and I can make this 100 times or 1,000 times, and then it might adjust better. But what we basically want is something smarter than just run it a couple of times. So we basically want to keep learning unless we don't learn any new information anymore. So we're basically going to make this a while loop, and we're going to say repeat while we are not finished. And to determine if we're finished, we're going to get these mistakes that we create here in the teach function. So here we're going to return the list of mistakes. And then we're going to create a variable mistakes, which is a list of mistakes that we're going to initialize with an empty array. And then the mistake here, we're going to append, mistakes. We're going to append the mistake that we've created, and we're going to return it. And then we need a variable here, which is the mistakes. And we're going to get that out of the teach function. Mistakes. And now we need to implement this is finished function. So let's do that. Func is finished. That will receive a list of mistakes. And it will return a Boolean if we are finished or not. So for this, we are going to first calculate all the errors of these mistakes. So we're going to get the errors out of here. And for this, we're going to map all the mistakes again, and we're going to sum all the error values that have been accumulated in these mistakes. And then we're going to calculate a mean, which is a root mean squared error. This is the third function that I showed, which is basically a nice way of calculating from a set of errors a single mean value. So there's a bug still here. We need to sum the errors. Yeah. So now we're keeping track of this mean. And we basically want to compare it to the previous mean, and if it doesn't update, then it will. Then it means that we don't actually learn anything. So we're going to guard a previous mean which is pref, which is a variable that we're going to define outside of this function, which is a optional double, guard let. And if we didn't have one before, we just return false, but not before we set the previous value to the mean that we currently have. And if we have a previous mean, then we need to set the pref to the mean as well. But we can calculate the difference, which is the absolute value of the previous mean minus the mean. And now we can return if the difference, so if the change in stuff that, if the change in errors is small enough, in this case 0,0,0,0,1, then we're going to stop learning. And now you see that if I run the algorithm, it already starts running longer because it's now updating until the difference isn't changing anymore, and we can here see a nice visualization on how the difference sometimes, like it learns a little bit quicker and then it goes down a bit again. And if you look at the mean, you see that the mean almost always goes down, but with different steepnesses. And then, oops. You see that the weights that get learned get like the lines get thicker, which means that the weights are higher on this, and then some are negative and some are positive. And then if it finishes, you'll see that the output of the network will be what we expect. It actually isn't. So this can have two causes. One is that the implementation of the network isn't correct, which I'm going to verify just now. And one is that it matters how it initializes the network. How the weights, you see that the resulting network every run is just different because it starts with different values. Let's try it one more time, and otherwise I have prepared for this. So I already have like a implementation here of what we've created here. So that's, oh wait, I can probably just take this one. Yeah. Oops. And just paste it in here. Come on. So now it's running again. The visualization broke because I copy-pasted it. Well, let's see if it works, and otherwise I'll move on to the next example. What I've shown here is like a fixed set of data, right? So it's just like these Boolean functions that we know of, and we can implement them better than in a neural network. So what I want to show next is actually more real example, which is like I brought these playing cards. And what we're actually going to do is basically detect the color of these playing cards, or learn the color of these playing cards, and then from that basically distinguish them between red and blue. I don't know why this isn't working. what I've done here is created a little view that has a camera, and then on top you see the left. Like it basically takes the center, like it detects the center of the card using Apple's frameworks, and then picks a color from that. And if I here tell it to teach, then it will basically run these colors through the network. And then if like we can see that here, if the difference actually doesn't change so much, so let's run it again. You see here that the data is much noisier. And then it will actually, like if the difference doesn't change much, then it will stop learning. And now I can basically predict and ask it basically like, okay, what do you think this card is? And here you see like it detects, like on the bottom, you see it detects a red color, so it thinks it's heart. And here you can see that it detects a black color, which is spades. So this is a more real example. This is still like just one basic, like the inputs and the outputs of this network are the colors that we have in, sorry, the one single color that is detected from this card, which is split up into 3 components, red, green, and blue. And then we're creating 2 examples here to get out of this, and then we're using this teach function to teach this example again. And then when we start predicting, we're asking the network what it thinks it is, and then it will return the outputs. So this is basically what I had. Thank you very much for your attention, and I'd love to answer your questions.
Perfect. Do we have any questions for Niels? Yes, Xavier. You can just talk, you're good.
Yeah, okay. Thanks a lot for the talk. It's very, very interesting and very nice to have you live coding again. My question would be regarding neural networks. So you can have like as many layers as you want and as many neurons on each layer.
Yeah.
Do you have a rule of thumb or some hints on how to choose how many layers you're going to have or how many neurons you're going to have a good output? Or is it just, and...
The answer to that is like the answer to a lot of questions, which is it depends. So it all depends on your data, right? So here we had some basic Boolean operations or just some functions, or just some colors that were some outputs, and the problem at hand basically kind of steers you towards, or like can inform you about what you can expect for how many layers you want, how many nodes you want. And this also changed over the years, because like 10 years ago they were like with tens of like nodes in the tens or the hundreds were already really big, those networks, but now they're in the thousands or millions. And then I've shown like fully connected networks here now, and you can also like steer the network a bit by not connecting all the nodes to each other with weights. And this is basically like being in the field of artificial intelligence. You get a sense of like what should work and what not, but there is no basic rule or basic guideline. What is like I said, like don't try to implement your own neural network, but just take a library, but also don't try to learn your own neural network, because there are many instances of actually trained neural network on, for example, image data, and you can basically take those and then use a technique called transfer learning, which is basically like taking those networks and then showing them your data, and because they've already seen a bunch of images of pictures of stuff, they can actually more easily train on your data too. So like you can go that approach as well. So.
Thank you.
Yeah, yeah, one over there.
She can see you.
Hi.
Hi.
Yeah, hey. So I've actually been doing something very similar to this, like sort of entry-level tutorials on this sort of thing.
Uh-huh.
One of the things I was trying to work out was, if I have like a big array of data, like I guess for an image, it could be like all the pixels in the image, or if you're doing some like agents, then it's the position of other agents.
Yeah.
Would you have to have like inputs which are dynamic based on the sheer like number of agents you have, and then you might have like their multiple points of data per agent, and then your inputs gets Titanic? Or are there ways to like iterate over a set of similar data? Like, are there any keywords to search for on that sort of topic?
So the there are cases where people actually adjust the amount of nodes in a network, but most learning algorithms learn with a fixed set of networks. So then you're basically looking for a representation of your data that can, well, basically sometimes doesn't use all the nodes, right? Or all the inputs to pass data to. If you're talking about more temporal data, so like a sequence of things, like an agent that has like a certain position or something like that, it might be worthwhile to look into recurring neural networks, which are basically things that feed input into itself again. So basically, outputs get into the input, it gets to one of the inputs again, which allows it to basically store some information inside of the network while it's running, instead of just learning once and then have inputs and outputs. And then there's LSTMs, which is basically, it stands for long short-term memory, which is basically like another type of architecture where you have basically a learner cell that can like keep a certain amount of data and output that again. So like you could look into that for these kind of things. Yeah, no problem.
Perfect. Could we show Niels our appreciation? Perfect. Thank you.